I recognize several of you in the audience who've been to our Distinguished Scientist Lecture Series. This is a fairly new series, as you know, that Don Powell, our Earth Science Division Director, has started to bring eminent scientists to the Berkeley area to talk about contemporary Earth science research. So I think this is a perfect example, and we're really look forward to hearing this. Before I introduce Jerry, I'd like to mention that another objective of this seminar series is to allow our distinguished scientists to interact with the folks in the Berkeley area. And to that end, we have a very busy schedule for you today, and we also have a brown bag lunch set up that's open to everybody. Can you hear me? That's open to everybody that Ying Ying has arranged at the cafeteria, correct, Ying Ying? And so we particularly encourage students and postdocs to attend, but basically if you go to the cafeteria, go through the checkout cashiers and then go down the stairs, and it's that room there, and you'll probably have some signage, correct? All right, so welcome Jerry. Jerry comes from Iowa, where he got his bachelor's in chemical engineering. He went off to Texas to get a master's and PhD in environmental health engineering and civil engineering, respectively. Returned to Iowa in 1977 to the College of Engineering, where he's currently a professor. And I'm sure most of you are familiar with his very broad and very deep background in research interests and expertise that involves all environmental topics, studying soils and water, but a real deep focus in environmental remediation, particularly phytoremediation, water quality monitoring, and more recently he's been interested in working in carbon sequestration and bio topics like we'll hear about today, biofuels. So Jerry has a very impressive CV, and he has been involved in really too many panels and professional committees and awards to mention, but I should say he was elected to the National Academy of Engineering in 1999 for his work in mathematical modeling as informing science policy decisions. He's chaired U.S. EPA Council and is currently on the Scientific Advisory Board for the U.S. EPA as well as the NIH Advisory Board. And I think many of us know him as the current editor of Environmental Science and Technology. So please join me in welcoming Jerry to give this talk that's focused on biofuels, energy security, and management options, which I think will have a real interesting policy flavor for us. So welcome, Jerry.
Thanks, Susan. It's great to be here, and thank you for that kind introduction and for the invitation. I have a lot of friends here at UC Berkeley, but I've never been to LBL, or I guess we're supposed to say LBNL now. And it's really pleasant to be here, and I'm looking forward to getting to talk with people this afternoon. I am doing research in the biofuels area, but mostly it has to do with life cycle assessments. The talk today, as Susan said, is more policy oriented, and I thought I'd try to explain what I see is going on in the policy arena for biofuels and broader questions too, energy security, issues, and kind of we'll touch on a little bit what the states are doing, at least in the broad hinterland of the Midwest where I come from. I'll tell you what states are trying to do to address these issues. We'll start with the climate, and just a few slides on maybe the impetus for why I think we are making progress on biofuels and energy security issues, and why it's going to continue to be that way in the future. If you had just gone to the doctor and this were your blood gases or something like that, I would submit that you'd be pretty worried about your health, and indeed it is a very strong environmental signal. The Philistines among us may ask, though, so what? The carbon dioxide concentration in the atmosphere, it's a trace gas. Is it really doing anything? But for many reasons, we know this is caused by us. There's no debate about that. The signal began to rise just at the beginning of the Industrial Revolution in the 1800s, so the timing is right. The amount, about 2 parts per million each year, almost 388 parts per million this year, and 2 parts per million more next year, and 2 parts per million, and 2 parts per million. The amount can be completely explained by our own emissions. It's roughly half of the accumulation of our emissions each year, and of course we think about 30% of that goes into the oceans, and probably the remainder goes into the terrestrial biosphere. So the timing is right, the amount is right, it can be completely explained by our own activities, and the dynamics are right. By tracers and even by aircraft missions, we can see the CO2 mixing from the northern hemisphere and its emission sources to the southern hemisphere. We know for sure that this is due to us. Of course, the question is, how much does this influence the temperature? And while it's a fact that any molecule with more than 2 atoms, 3 atoms or more, can vibrate and rotate and absorb back radiation, CO2 is actually one of the weaker ones, but it's at fairly high concentrations now. And as you know, this is the famous Vostok ice core. It goes back 450,000 years. We have another core that goes back 650,000 years now. And this is a direct measurement of CO2 from the gas bubbles in that core. And of course, this is an inferred measurement of O18 isotopic ratios for temperature. And the two mirror each other very well. I submit that if you look really closely, I think you can convince yourself that temperature actually precedes CO2. So we believe that Jupiter and Saturn are large planets with irregular orbits that exert a large influence on Earth and causes 3 different kinds of eccentricities and wobble in our planet and our orbit, which throws us into and out of an ice age. Here we have ice age, ice age, ice age, interglacial period, about every 100,000 years or so. But what's different and dangerous about the experiment that we're running, as you know, is that now we're leading with CO2. That's unprecedented, leading with CO2. This slide is already a little bit old. It should be maybe 386 or 388 parts per million now. And this is unprecedented in this geological history. And in a way, I like to say that on the expanded axis here from 1900 to 2000, we're sort of waiting, in a way, we're sort of waiting for the other shoe to drop. We're waiting for the temperature to rise in response to this large increase in CO2 that we've committed. And it will rise. It is rising and it will rise because the gases last, including methane, quite long in the atmosphere. CO2 as much as 100, 125 years. Each year that it's up there, you can sort of think of it that the temperature warming that we're experiencing now is from the emissions over the last 100 years. Because each year it remains, it warms the Earth further, and there's a big lag associated with what we've already committed to. About all you can do, I suppose, is put your best estimates, the equations of momentum, heat, and mass transfer into general circulation type models, and there's more than 20 groups around the world that do that and are being tracked by IPCC, as you may know, and all 20 models agree that it's going to be a much warmer 21st century. What they don't agree on necessarily is how much warmer, and of course that's important, and that's responsible for the uncertainty in these projections that you can see here at various scenarios. If we could stop emissions entirely, anthropogenic greenhouse gas emissions, which of course we can't, but if we could stop them entirely, we'd still have warming because of the time lag that I mentioned earlier, maybe about 0.6 degrees Celsius warming that we're already committed to no matter what. Of course, we can't stop the emissions completely. So right now we're following basically a little bit greater than this A2 scenario. We're on a path for 3 or more degrees Celsius warmer in the next 100 years, according to the 20 models. Now in IPCC third assessment, the 2001 assessment, the target was sort of stated as being Well, if we could keep it at 550 parts per million, which would sort of be this blue-gray line here. But in the fourth assessment, the more recent reconnoitering of scientists, it's that we actually need to stay somewhere down at the bottom of this envelope of uncertainty. Oops, sorry. Oh, wow. I accidentally hit the wrong button. That we need to stay down around this bottom envelope here. And that would be below 450 parts per million. If we want the Arctic ice, the floating ice in the Arctic to remain, we, according to the climate models, we need to turn back the clock and go back to maybe 325 to 340 parts per million CO2, well less than we have right now. So we're already committed to the Arctic ice melting as well. Of course, the sobering point here is that in order to do this, you need a cutback in emissions of maybe 60 or 70%. In order to do maybe the bottom of the envelope there, the 450 parts per million, you need a cutback of 80% or so globally. So that leads me to think that we need a whole new way of doing business. We have to transition out of the fossil fuel age. When I talk to my students, I tell them that if I only had one slide to show, an elevator speech, so to say, I'd show this one to kind of tell the biogeochemical story of what we have done and what we are committed to. The magenta, these dark figures are how much oil, gas, and coal have already been combusted during the Industrial Revolution in billions of metric tons of carbon on the left axis, and what that would translate to in the atmosphere in carbon dioxide over here. We've burned roughly 1 trillion barrels of oil, and we've got a little more than 1 trillion barrels of oil in proven reserve. Maybe if you look hard enough and go deep enough, there might even be another 1 trillion barrels of oil in unproven reserve. And natural gas, likewise, we've burned less than half of what's out there. We're not going to run out of oil or gas in our lifetimes or our children's lifetime. In fact, my climatologist friends don't even worry too much about the burning of the oil and gas because they're already a scarce resource, and they feel that price will control the use of those resources and that we won't whole hog burn the remaining amount of oil and gas. But what they worry about the most is this one, as you can imagine. This is the coal that we've burned since the Industrial Revolution. If you add all these up, you can see it amounts to something a little more than maybe about 150 parts per million of CO2. That's about right because roughly half of it has accumulated in the atmosphere. And this is the remaining reserves, two different estimates. But if we go here, if we begin to burn the coal, and of course India, China, US, Russia have plenty of coal reserves, cheap coal reserves, and that's a big threat. If we go here, we're going to fry. So one of the messages is, the take-home message is you can't, we can't commit to any new coal-fired power plants. And we haven't even talked about the methane hydrates and the shale oil and tar sands, which is another immense carbon reserve. These things took 500 million years, roughly, to form in the Earth. 500 million years, and we're successfully burning them up in just the blink of an eye in geologic time in just a couple hundred years. Of course, if you take a carbon store that formed over 500 million years and you try to release it back to the atmosphere in just a couple hundred years, of course you're going to change the atmosphere, and we are. So we're approaching some tipping points, and I think the tipping points are kind of lost on Americans anyway, and they're very serious tipping points. We're headed towards a IceFree Planet. We can talk more about that if we have time. We have more severe storms already, it looks like, as a result of more energy to dissipate, We worry about sea level rise, not so much the thermal expansion of the ocean, but rather the possibility of abrupt climate change and ice on land, like in Greenland and Antarctica, slipping off into the ocean. Species extinctions as well, reversal of North Atlantic thermohaline circulation. And I have friends who are quite worried about the clathrate below the permafrost in the Arctic region being released to the atmosphere in a rapid fashion as a positive feedback loop. Enter the idea of biofuels. Where does this fit in exactly? Well, if you think about energy security, and I would submit that energy security and energy independence is much bigger on the minds of Americans than climate change. You may have seen Pew did a recent poll, listed 20 issues, 20 problems, and climate change was rated by people in America as number 20 out of 20 in terms of the need for action, I'm sorry to say. But energy independence and energy security is quite high on folks' mind in Washington and the general public. So if you think about energy security, it's really a problem of transportation fuels. We import petroleum. There is some diesel used for home heating, but mostly we import petroleum in order to fuel our cars and trucks and so forth. So if you could solve the transportation problem, you'd take care of part of the greenhouse gas issue, and at the same time, and more importantly, in people's minds, at the same time, you'd take care of the energy security problem. So I'm pretty convinced that biofuels are here to stay. I want to make the case, I want to show you that I think the way we're doing them now is not sustainable, and that hopefully we can use it as a bridge to a better place for biofuels. I had the good fortune to chair a committee actually in the end of 2007 on this particular topic for the National Research Council. I'll tell you a little bit about those results and go beyond those more what has happened in the last year or so. This committee worked especially on the water implications of biofuels. I'll talk about that and maybe some of the other greenhouse gas and energy implications as well. We heard testimony from a lot of different people. I learned an awful lot, and it was an interesting committee to be on. They covered the topics of the impacts of growing the crops, both in terms of water quantity and water quality, the impacts of the production facilities themselves on water resources, and touched a little bit on sustainability issues. And that's what we'll do here today as well. The more recent story in the last year or so is that of food prices and the impact on poor people throughout the world as a staple like corn or maize prices increase. But there's a lot of different things that one can do with corn and that we've been doing with corn. And they're listed here. You can produce starch or food type quality. You can produce corn sweeteners and flavor all our foods with it, and we're doing a fair amount of that. You can produce ethanol. You get about 2.8 gallons of ethanol from a bushel of corn and these different byproducts. You create jobs with it. That's real positive from the perspective of the legislators in the Midwest. And on the other hand, you may have an impact on corn prices, at least some impact. Most economic studies would indicate 10 to 20% of the increase in commodity prices that we saw at the end of 2007 was due to biofuels. A lot of it had to do with the weakening of the dollar at the time and the price of oil at the time as well. These numbers are changing so fast, but how is our corn being used today if it has all those uses? Well, a little more than a quarter is going into ethanol at the moment. There's still 7% in corn sweeteners, 13% in food. Animal feed is decreasing basically as this goes up, It's about 45% at the current time, and export is decreasing at the current time as this goes up. Now, you'd like to think, I guess ideally, if you're a technological optimist, you'd like to think that the corn yields could increase fast enough to both satisfy corn as a food and feed crop, and also to provide fuel for biofuels. And yields are going up, as you can see on this slide, but they're not going up fast enough. I live in Iowa. In 1995, there were no genetically modified crops anywhere in the world. Now in Iowa, we're in a sea of genetically modified beans and genetically modified corn. I like to joke with the students that here we are, you know, living in a sea of GMO crops, and we're perfectly normal. And but at any rate, the yields of these crops are amazing and going up very fast, but not at a rate necessary to produce the biofuels that Congress has mandated under the Energy Independence and Security Act of 2007. So we can't yield our way out of it. We've got to, that means more land is going to be required if we can't increase yields fast enough. And that is what indeed is going on. As you grow more and more corn, you have to get the water for it somewhere. And you can either get it, of course, from rain-fed agriculture, from precipitation, or you can irrigate the corn from surface waters or from groundwaters. And our country, we're doing some of all of that. These are the way the farmers feel like now, right now. Like it's easier for a camel to get through the eye of a needle than the farmers to know what to do, and they're feeling really worried and put upon because on the one hand they have this, like Blagojevich would say, this thing is golden, you know, and I'm going to do something with it. They have the food security issue going on and the biofuels going on, but on the other hand, there's so much uncertainty at the current time over greenhouse gas issues and indirect land use issues and the total life cycle assessment, how these biofuels are going to be assessed by EPA and, for example, by the state of California as well. Do they qualify as renewable fuels? Do they qualify as low carbon fuels? The verdict, as you know, is still out and people are worried. Of course, Congress mandated that we have 36 billion gallons of biofuels. We're at about 9 billion gallons right now. EPA has set a rule that we have about the 2009 Biorenewable Fuel Standard is that producers and blenders have to provide us with about 10% of our fuel as, quote, renewable fuel and have to certify that. I saw the preliminary report of EPA at the end of 2008, which under the Obama administration got rapidly sent back to EPA. So this is part of the uncertainty right now that has farmers and producers so worried. But in that preliminary report, existing biofuels after December 19th, 2007, I think it was, are grandfathered in. And I think that'll end up being all biofuels to the point of where the rules are issued will be grandfathered in and certified as renewable regardless of their life cycle greenhouse gas assessment. Are you with me? But the farmers worry a whole lot about then going from 9 billion gallons to 15 billion gallons of corn to ethanol, whether that'll be certified as being renewable. And of course, if it's not, the investment won't be made. The whole thing will go down. It looks like they're going to require something like a 20% improvement in the life cycle of the new biofuels in greenhouse gases based on a baseline of 2005. And that we don't have any yet, but the second generation biofuels, probably cellulosic biofuels, will have to be even better still, maybe have a 50% improvement in greenhouse gas life cycle emissions off of a 2005 norm or baseline period. Europe is doing much the same, but Europe is basing it, they're comparing everything to gasoline instead of off of a 2000, but in the end, the rules, you can compare the different rules, and Europe is a bit ahead of us. They've just issued their rules. EPA also and Europe are interested in indirect land use being included in, and this is part of the big uncertainty, as you can imagine. I think you could argue either way, but the notion is that with 6.7 billion people on Earth, we need food, feed, and fuel. Well, the food and feed is not going to go down. So if you begin to use corn for fuel, you could reason that means that land somewhere in the world is going to have to be cleared and used for corn in the future. As soon as you clear savanna in Brazil or marginal lands in Iowa, you open the land up, and of course there's oxidation and loss of organic carbon and CO2 to the atmosphere when you do that, and that works mightily against this rules of getting a 20% or a 50% improvement. Probably they wouldn't qualify if you put the indirect land use into the equation. So that's really controversial. EPA is getting lobbied hard right now by a lot of different, from a lot of different places, that indirect land use should not be in the life cycle greenhouse gas assessment. It's not the only problem with the way we're doing biofuels now. I'll show you some other issues as well, but it is a major problem how you assess that. If you instead say that, remember I mentioned that the corn price, most economic studies would indicate that the price of corn when the commodity went way up was only 10 or 20% controlled by this. That argues for a much more complicated picture, and that other issues of market and substitutable crops and play a much bigger role than how much biofuels are being made, and that therefore indirect land use should not be in the equation. But that's the big issue, and maybe we can talk about it too. I'd love to hear what you think about it. Coming back to the water, we are producing the corn from both irrigated agriculture as well as rain-fed agriculture. Much of the so-called corn belt in the Midwest is mostly rain-fed agriculture. They have deep soils left over from the prairie, and it's really a remarkable situation, maybe reproduced nowhere in the world but perhaps the Ukraine, where you have just enough deep soil, storage capacity for moisture, such that when it rains, let's say maybe only every 2 weeks in July, there's enough storage capacity for soil moisture for when the plant is pollinating at that crucial time that it won't wilt. Very few places in the world have that, what the economists would call comparative advantage, and this part of the world does have it. So they're par excellence, they have a comparative advantage for growing corn. My economist friend said, this is really nuts, you know, this is the best place in the world to grow corn and the most efficient. We should be growing corn, selling that to Brazil, and in turn importing Brazilian ethanol, because they have a comparative advantage for producing ethanol. They're in the tropics, they're using the sugar cane plant, they're getting about 900 gallons per acre. I've got to convert their numbers. About 900 gallons per acre of ethanol, where we're getting 400 or 500 gallons of ethanol per acre in the Midwest. And that's because they're using the entire sugarcane plant. They're in the tropics. It grows well there, better there, longer season. And they're also, as you know, efficient because they use the bagasse to power their plants, where we use coal or natural gas to power our manufacturing facilities. So for all those reasons, Brazil's more efficient in terms of producing ethanol, but we have a 54 cent a gallon tariff against Brazilian ethanol. It's designed to offset the 51 cent a gallon blending subsidy we have for our own ethanol, so that they would be on a, that's the rationale anyway from Congress. Well, we're also producing it here in these orange areas and in the Central Valley of California where it's being irrigated. And more irrigation here, 4,000 gallons per bushel, about 2,000 gallons per bushel here. You may recognize this area in Nebraska, Oklahoma, Kansas, Texas as being the Ogallala Aquifer. Aquifer once equal to Lake Superior in size, something like 5% of the world's fresh water, but we've pumped it down already more than 100 feet. Imagine we're using a 51 cent a gallon subsidy, billions of dollars of subsidy to pay people to pump down the aquifer, and that's exactly what we're doing. In fact, if you look at these black dots, the bigger the black dot, the larger the ethanol production facility. And if it's a 100,000 gallon per year ethanol plant like this black dot right here, that's using the water equivalent to irrigate the corn of about 2 million people in terms of population equivalent. So that's 2 million people, another ton of 2 million people, 2 million, 2 million, and you get the picture. It's an immense water requirement to irrigate the corn to produce the ethanol for our biofuels. Having said that, it's not to excuse the other ethanol production facilities. By the way, don't think that taxes and tax credits or subsidies don't work. Policy really can work if it's created wisely. The states with the most ethanol production facilities are my own state, Iowa and Minnesota, and they also have, and Nebraska, and those three have the highest state subsidies to go with the 51 cent a gallon ethanol blending subsidy, and so it's no wonder that they're the place where, in addition to the corn being there, they're the place where the ethanol production facilities are located. Each and every one of these, most of them are drawing their water from glacial aquifers. And to give you some idea of what we're up to, in western Illinois, the Cambrian Ordovician aquifer has already been depressurized. That's a confined aquifer, depressurized about 800 feet or so. So we're doing the same thing as the Ogallala in the confined aquifers in order to satisfy the water demands for these ethanol production facilities. Of course, the really big water use is for the irrigation, but the facilities themselves also require a lot of water. About 4 gallons of water per gallon of ethanol is typically required. I thought I'd show you one little plant that you might like to see it. This is in Boone, Iowa, not too far from Ames, Iowa State, my alma mater. It's using 18 million bushels of corn. That's about 100,000 acres of land to supply this little facility, 100,000 acres, with corn in order to make 50 million gallons per year of ethanol. And they're using about 200 million gallons per year, and it's from a glacial aquifer source. Kind of a typical setting, and one that I thought you might find interesting. You need really high purity water in these ethanol production facilities. That's in order to, for the fermentation process, the liquefaction and the fermentation, you need high purity water, so that means you have to do reverse osmosis or ion exchange in order to get that high purity water. And the brines, the reject water, is an issue of what to do with that. We have to get NPDES permits in order to discharge that reject water. And sometimes those permits are in violation. But basically you get, sorry, I did it again. Basically you get two products out. You get dry distiller grains, which we mostly are selling to California right now. That's an animal feed from the oil and the protein that remains in the bottom product. And of course you get good old 200 proof ethanol, which they blend with 5% gasoline. So people like my students won't drink it, right? Well, the ethanol production facilities, like your state and like any state, everyone's trying to create jobs and recruit industry to the state. Many industries, many manufacturing industries use a lot of water. Ethanol production facilities also use a lot of water, more than the average industry. And if you want a production facility like this, typically 100 million gallon a year facility, it's equivalent, in a population equivalent to a town of about 5,000 people. So it's a big water demand, but it's at a point rather than the large irrigated footprint that's required to grow the corn itself. Corn is unfortunately a really high intensity, high input crop, as you know. This is, Dave Tillman was on our committee for this NRC assessment, and this is from his paper in Science a couple of years ago, showing that no matter how you're going to try to make an energy crop, corn is probably the highest input way of doing it. In terms of fertilizers, kilograms per hectare, this is the phosphorus and nitrogen requirement for corn versus beans versus grasses or woody crops. This is the requirement of pesticides versus beans and so on. And so this is probably one of the worst crops you could choose as a feedstock for our biofuels industry, if you accept that, you know, we really are, biofuels are here to stay and we're committed to this. It's probably the least good crop to choose. In the Midwest, the water quality impacts are great. In certain locations where corn is the predominant crop, nitrate concentrations are still increasing in our rivers. And you know the maximum contaminant level allowed for drinking water is 10 milligrams per liter nitrate. And you can see that we routinely exceed that. In fact, the town of Des Moines, the city of Des Moines, has to have anion exchange process for nitrate removal in order to treat this water for drinking water purposes. Now, there's been economic studies made, and I'm sorry to report that this is the much cheaper to remove the nitrate from the whole river for drinking water than it would be to go up onto the landscape and make best management practices and remove it at the source. And so that is what we're doing right now. We're removing it from the river in order to continue to use the water as a drinking water source. Of course, where you have permeable soils and you're applying this much nitrogen to the landscape, you end up with high concentrations in the groundwater, which, you know, stands to reason. And you can see that particularly where we have sandy soils in western Iowa and southern Wisconsin and so forth, and eastern Nebraska, we have real high concentrations in broad swatches of surficial aquifers. Not all of the nitrogen and phosphorus ends up in the groundwater or ends up in surface waters in the Midwest either. A lot of it ends up running off into the Gulf of Mexico, and our yields are roughly about 1 to 10% of what's applied is lost. That's at great cost, you can imagine. Last year, ammonia was, anhydrous ammonia, which is what we apply, was $1,000 a ton. So when that runs off, that's a huge economic loss. And you can imagine that the people in Louisiana aren't too happy, and they're not. The Gulf hypoxia is a big issue. We have a national goal of reducing this 20,000 square kilometers of Gulf hypoxia, the so-called dead zone, by reducing it to 5,000 square kilometers. But because of biofuels, it's going the other way. We're not only not reaching the goal, it's getting worse and worse, with no real plan for how to recover the coastal waters. I have a project with Nancy Rabelais and Gene Turner. This past year we had huge floods in the Midwest. Iowa River and Cedar River in particular flooded, and we got a small one of these sugar grants from NSF to follow the floodwaters from our Midwest all the way down to the Gulf of Mexico and try to understand what's the role of the floods in transporting nutrients and exacerbating Gulf hypoxia. And this is my student Aaron Gwinnett, who's working on it. I don't know if you can see it, but this is the Mississippi River waters here coming out. They're dark brown, chocolate brown, and this is the Gulf of Mexico waters. So this corn that's being raised, how does it shape up from a greenhouse gas or an energy standpoint? And there have been so many papers. I'd venture to say that in my journal alone, we're now publishing something like in ES&T, almost 10% of the volume of the journal is in life cycle assessments of various products and processes. Not only this, but of various products and processes. This whole notion of trying to judge is A better than B from some metrical standpoint is a new enterprise in our field of environmental science and engineering, and occupying an awful lot of people and time and research. In terms of the corn, you would worry about what are all the energy inputs to growing the corn from a life cycle assessment. You'd worry about how far to peel the onion, you know, where do you stop the boundary analysis of that life cycle. And you'd worry about, if you're a energy security advisor, you'd worry about where does that energy come from. Is it imported or is it not? And how much greenhouse gas do you get when you burn it or not? And so here you can sort of see that to drive the tractor through the field, actually the GMO crops, one of the reasons the farmers adopted it, they hate Monsanto, and they hate signing contracts for, on genetically modified seed and not using it. They hate it. They're very independent, but they do it. And if you really ask them, you know, why do you do that? And I have a lot of farmer friends. The main reason is that because their margins are so razor thin, agriculture is probably the most competitive industry in the world, I would say. Because their margins are so razor thin, they all think they have to get bigger and bigger. And in order to get bigger and bigger with the same equipment, you have to have fewer and fewer passes through the field. Well, the GMO crops, the BT corn, and the Roundup Ready beans allow you to make fewer passes through the field. And that's the main reason why they actually have adopted it whole hog. 75% of our crops are GMO now in the Midwest, and that means less diesel, but it does still require diesel for the tractor to go through the field. The corn requires anhydrous ammonia. In Europe, they don't use anhydrous ammonia because it kills all the worms, but it's the cheapest form of nitrogen, as you know. And so in the Midwest, we're still using anhydrous ammonia, and that comes from where? Natural gas, right? The Haber process. A lot of this is imported. Not all of it. So some of the natural gas we're making here, some of it we're importing. The thermal energy, the plants are being run in Iowa mostly on coal-fired power. I tried to convince our governor very hard to say no to a new coal-fired power plant we have proposed right now, but I couldn't convince him. And the reason I couldn't convince him is because the coal-fired power plant is needed to fuel to provide electricity for all the ethanol production facilities that we're building. So it's a wholesale transfer of, it's basically coal to ethanol, to transportation fuel, which the Energy Security Advisor would love because it's national coal to ethanol. But it's too many greenhouse gases, so that's why I object to it. And we also use natural gas as well in the processing. If you look at the ratios from all the different viewpoints, from just the motor fuel energy out divided by the feedstock energy, now this includes the sun here to grow the corn, as well as the process energy to make the, to grow the corn and to make the ethanol, versus an environmentalist who would worry mostly about the motor fuel energy out compared to the fossil fuel energy in, because this represents the greenhouse gases that are going to come off, versus a national security advisor who would worry about the motor fuel energy out divided by the imported petroleum in, assuming all the petroleum is imported here, you end up with much different ratios. And maybe this is where all the controversy stems from. For the environmentalists, I looked here at 14 different studies, several of which were from ES&T, and you get about 30%. It ranges all over the place, to be honest. But if you take the median, you get about 30% more fossil fuel energy out. Motor fuel energy out than the fossil fuel energy. So it's marginally renewable in terms of greenhouse gases, and it's marginally favorable in terms of energy output on this basis. If you just worry about how much imported fossil fuel went in, it turns out much better. So this is the people who think fossil fuels are here to stay, and corn to ethanol is a perfectly good way to make it. Of course, we're still not off the hook, even because of indirect land use and because of nitrogen emissions. In that previous slide I showed you, there was no accounting for N2O gas, which comes from all the nitrogen that we put on the land when it partially denitrifies. And the N2O, we have recent studies, Schultz and Eisenhardt at Iowa State. Paul Crutzen had a very interesting paper recently in Atmospheric Chemistry and Physics, the European Geophysical Union Journal, showing that if you count the N2O coming off of the corn crop, that it may throw the whole greenhouse gas balance negative instead of positive. And that's because in the workbook for IPCC or EPA, we assume the default value is 1.25% of all nitrogen applied goes off as N2O. But our recent studies indicate that it's much, much higher than that, 4 or 5 or maybe even 6% of, it depends on the soil moisture and the particular year, as you can imagine. But much higher fraction, maybe 4 or 5% of the nitrogen that's applied goes off as N2O. If you count that into the life cycle greenhouse gas assessment, ethanol goes south. And so that's a big issue. And that doesn't even include the indirect land use issue of Searchinger and Fargione. If you take both of those into account, it clearly doesn't pass the muster as a renewable fuel. Of course, if you farm wisely, you can store carbon in the soils as well. I just wanted to mention that. And if you have switchgrass, a perennial grass, you can store an awful lot of carbon in the soil and still harvest the crop for ethanol production, say, with cellulosic biofuels. If you have no-till corn, you can still store quite a bit of carbon in the soil and take credit for that. If you plow the corn, though, it's pretty hard to have a significant storage in the, and so in the life cycle assessment, you have to take this into account as well for how the corn is being grown. Well, Congress has mandated that by 2015 we move towards 15 billion gallons of biofuels by basically 1 billion gallon from soybeans to biodiesel and 15 billion gallons from corn to ethanol. So that raises the question, if we're at 9 billion gallons now, how are we going to get from 9 to 15 billion gallons? Well, this is the projected amounts that would take us very close to 15 billion gallons. And Iowa says they're going to double their amount. It's almost all our corn will be devoted to ethanol production at that point. If we go any further than this, we'll be a corn importing state in order, honestly, in order to feed our animals. We'll be a corn importing state. But we're currently at about 2 billion gallons. We say we want to go to 4 billion gallons. I don't know how in the world Nebraska is going to go to 3 billion gallons with their irrigated agriculture. The Republican River has already gone dry. They've already pumped the Ogallala down a lot. And so I don't know how they're going to do that, but that's their stated. And if you add all these up, you get very close to the 15 billion gallons. But the question remains, will EPA certify that these new biofuels from corn to ethanol are renewable fuels or not? And if they do not certify that, all bets are off. We haven't talked too much about the so-called second generation biofuels, but I thought I should mention that everyone thinks they'll be better from a life cycle greenhouse gas assessment than what we have now, and substantially better. They'll use less water, they'll use less energy inputs, and they'll use far, far less pesticides and nutrient inputs. How it's going to look, I don't think anybody knows. There's more than that, but two basic competing processes. You can go with biological fermentation. Most people think that with biological fermentation of cellulose, you have to have pretty much homogeneous feedstocks because the enzymes in the organisms are very finicky. So you have to have kind of a pure feedstock. And it might be miscanthus, we think, grows really well in the Midwest and South. Switchgrass. It could be corn stover, the residues left over from the plant, and this is kind of where it's starting actually. Or it could be a woody crop like poplar or willow, something like shown here. Of course, it could be more like a synfuel type process, which you're quite familiar with here at LBL. In a synfuel, it's sort of like gasification and catalysis. You can produce mixed alcohols. You can produce various products like biobutanol, which might be a better biofuel in the future. It's gas pipelinable. It's less corrosive. It's less volatile than ethanol in terms of air quality, which we haven't even had time to talk about. If we go towards thermochemical conversion, you could use, this is the dream of my friend David Tillman, who's on the committee, we could replant the prairies again. We've cleared 99% of the prairies in the Midwest. 95% of the wetlands have been drained. 99% of the prairies have been removed. 75% of the forests have been cut. So the dream is you could begin to resurrect the landscape maybe closer to what it once was. And you could mow it. You could use the prairie polyculture for making the cellulosic ethanol. That's one dream anyway. Where are we starting? Well, we're starting with the corn fodder, the corn stover, the residue left in the field, because it's easy for the farmer to, relatively easy, for the farmer to pick that up at the same time as they harvest the corn with the combine. So the corn could still go to making ethanol from the starch, and you could, from the cellulose, use the remaining material. Obviously, you can't take it all. Most of the studies would indicate that you have to leave 30 or 40% of the residue on the land in order to stop wind and water erosion. But I have to tell you, I'm skeptical of this. You know, the logistics have not been well worked out. Just the number of trucks, the storage of this stuff. You know, it only comes off the field once a year, and you've got to use it as a feedstock throughout the year, which means you got to ship it, transport it, store it, handle it. It's fluffy. It's not dense with energy like a corn kernel is dense with energy. It doesn't flow in a materials handling, from a materials handling standpoint, like a corn kernel, which is really a nice amount of concentrated energy in the starch in a corn kernel. We're starting with, we have one plant in Iowa. It's the Emmetsburg, the Bruin facility, and they're starting with, they've got a combine that picks up the, after shucking the corn, after taking the kernels off the cob, they collect the cob, and normally what the combine does is grind up the cob and blow it back onto the land in a diffuse form, but in this one you collect the corn cob and it's more transportable, and it's cellulosic, and you would use that for the first fermentation, and that's what we're trying to demonstrate right now, and with some success. We're still, I'd say, far away. My guess is 4 or 5 years away still from a commercial cellulosic ethanol process. just to show you what the prairies would look like, the dream of my buddy Dave Tillman. Woody biomass could be used too. You could even do it in stream margins if you wanted to try to have the farmer give up only a couple % of his land. He could still, or he or she could still have the main crop and be growing this in riparian zone and hopefully leaving the roots in place for better water quality of that stream. We had an economist on the committee, actually, who spoke to our committee, Dennis Ugarte from University of Tennessee, who makes a strong case that the future generation of biofuels will not be in the agricultural Midwest, but rather it will move south and east, following a gradient of plentiful rainfall, which is needed for the reasons I hope I've shown, and cheaper land. Our land is far too expensive in the Midwest, so that the new cellulosic industry will move down here into Kentucky and Tennessee and Alabama, and Mississippi, Arkansas, and so forth. Plentiful water and cheap land. Copy onto this the so-called stimulus bill and all the things going on, and I thought I'd finish up with just a little bit about what the states in my part of the country are doing to try to respond to both climate change as well as some of the other challenges of our energy system. $80 billion of the $787 billion are for things that we're very interested in this room, including energy efficiency incentives, yes, biofuels and renewable energy, efficient cars, a lot of federal government cars that run on biofuels, carbon capture and sequestration projects to prove that this technology might work, the so-called clean coal, if you believe there is such a thing or not. And $25 billion is for energy efficiency, $5 billion for retrofits and weatherization, $11 billion, which is sorely needed if we're going to use wind and solar. We need a better grid, as you know, in order to get the power from where there's rich wind and solar resources to where the people are. We also had, an extension of the wind and biomass tax credit 3 years into the future to 2013, which is a big deal for people who want to invest in that, and we desperately needed that. $2 billion for advanced battery research, lithium-ion in the Toyota Prius hybrid, which is supposedly coming out plug-in this year, is I think it's Japanese technology and manufactured in Korea, but we do have some leading battery technology here in the United States as well. My own state, Iowa, I was chair of our Iowa Climate Change Advisory Council, still am. 20-some states are doing similar things to what we are. California really preceded us, and we're shooting for a 50 to a 90% reduction in greenhouse gases by 2050 from a baseline of 2005. The governor has bought into this. By 2012, we have to turn we feel we have to turn the corner by 2012 because we've been increasing our greenhouse gas emissions about 1% each year. We have to turn the corner by 2012. By 2020, we have to have about a 10 to 20% reduction. We looked at over 300 options. We adopted 56 options. You don't need all the options. A lot of them are overlapping. There's so many ways to skin a cat, if you will. You can have carrots and you can have sticks. You can have tax credits and you can have taxes. You can have command and control legislation. You can have subsidies. There's a lot of different ways to change our environmental behavior and get the transition that we need from a fossil fuel economy to a more mixed economy of energy efficiency and renewable energy. Of the options that we looked at, I know you can't read this, but I'll just tell you this is the dollars per ton over here in cost saving, and about half of them would save energy and save money at the same time. Most of these are the energy efficiency type options. About half of them you have to look at as investments, much like when we buy a house and we figure that's an investment because we're getting something in return. When you invest in the grid or you invest in renewable energy that creates jobs. It's an investment. You get something back, this transitioning out of the fossil fuel, but it does require money, and that money has to come from somewhere, and it has a long payback period. I think the way it's going to go, I don't know, but I think the way it's going to go, this is a Toyota Prius plug-in. They're on the road already in London, and this is all the way to a hydrogen fuel cell car, Honda FCX. There's a few of them here in California. I've had the chance to drive one. It's pretty cool, actually. And I don't know how we're going to go, but we need gas mileage as well in excess of 100 miles per gallon. I'm encouraged that we can do this. I'm encouraged that we can do this because of the low-hanging fruit. You know, we really haven't even tried with our buildings. That's 40% of the greenhouse gases. We really haven't tried with our cars. That's 25% of the greenhouse gas emissions. And I'm pretty convinced that it's going to start with these plug-in hybrids and to some extent the second-generation biofuels. Why the plug-in hybrids? Well, you know, I envision that you'll drive your car into work and it'll be under a solar garage or shelter, and you'll plug it in during the day. The lithium-ion batteries take 3 to 6 hours to recharge, the current generation of them. And at night, you'll plug it in. In Iowa, when you plug it in, we have so much wind power, and it's relatively inexpensive. You're recharging your battery with renewable energy. That's what we need to do. We need to replace, we need a short-term storage mode for transportation for wind and solar in order for them to become transportation fuels. So that's what we're doing. We're essentially making wind and solar be our transportation fuel. Instantly, we solve the energy security problem, which is number one on everyone's mind, and we provide storage for intermittent sources of power like wind and solar, which is their biggest disadvantage and bugaboo. And this is a GM Volt down here, which is also, I don't know if I can fit in that thing, but that's also coming out in 2010 as well, supposedly. All our buildings, you know, any building that you build, it just seems to be a no-brainer that it's got to be super energy efficient in the future, and there's going to be a lot of investment in retrofitting as the American Recovery and Investment Act indicates. Our homes are going to be, I have a real hard time convincing my utility friends of this, but and this analogy isn't perfect, I admit, but they have the old paradigm in their mind of the last 75 years that we have to have a base load plant. You know, we have about 600 large coal-fired and nuclear power plants in this country, which are running the entire grid, basically. That's what's going on. And they just think that you have to have that base load capacity, and then, okay, wind and solar are fine up and down off of that. But I argue to them, no, it's going to be more like the internet. You know, do you have 600 large servers and supercomputers running the internet? Hell no. You know, it's going to be more, there's going to be millions of producers, you and you and you and me, and we're all going to be producing our own energy, feeding into the grid with data mining and data assimilation techniques, which we already know how to make that grid. We do need a smart grid with many, many thousands of more miles of cable in order to produce it. So your roofs are going to look like this. You're already doing it in California, Japan, Germany. Germany and Japan are two of the cloudiest places I've ever been in my life. They're doing it. Okay, there are subsidies, I admit, but they are doing it, and so are you here. This is a 5 kilowatt system this guy is installing. There's about 3 good systems to choose from, at least 3 good ones. You need probably 10 kilowatts for your house to be able to supply all your power and run the meter backwards occasionally. This is a home in California I just downloaded off of the web. I haven't seen any cars like this, but I guess you're driving cars like that in California and filling them up in your basement. Iowa wind power, we've gone whole hog into wind where We just passed up California as the second largest wind state. Now it's a very good resource there. We've got about 3,000 megawatts. It's 10 or 15% of our total power. I think only Denmark has more. Denmark's about 23% of their electrical energy is now coming from wind power, and they're having to deal with it. There's issues associated with that. At night, their power is almost free. Industry has to retool and figure out how to make use of that cheaper power, and we have to be able to meter it so we can credit people when they're using the cheaper power at night. Our wind blows stronger at night than it does during the day, and we're going to use that to fill up our plug-in hybrid vehicles. We have 5 wind manufacturing plants in Iowa. 2 more have just announced. We have thousands of green-collar jobs already with good wages as a result. If we're going to use coal, I wrote an editorial in ESNT, no new coal. I might modify it and say no new coal except for a few demonstration plants, which I'd like to see if it even is feasible, whether we can deep six the carbon dioxide in carbon capture and storage. The conventional wisdom is still that integrated gasification and combined cycle is the way to do that, because you can create a concentrated stream of CO2. You have to have a good place in order to store it. In Iowa, we have no good geological storage places for this CO2. It's denser than air, so you got to worry about it leaking or belching and suffocating everybody. And but we do need the research, I think, and we don't have it right now in this country. So I'd be all for pursuing it, but to me, no new coal unless you can show that you're going to be able to deep six the emissions. People do it, as you know, the coal field here is in the North Sea. Oil companies are deep sixing CO2. They're using it for additional pressure for secondary oil recovery successfully, and it is in a semi-liquefied state, in a critical state, and it doesn't come back. It seems to be stable so far. Cap and trade is coming. It wouldn't be the way that I would do it, quite frankly. If I were king, I would do a carbon tax, and I'd push the tax up to the farthest end of the producer. I think that's the fairest and sends a clear market signal immediately. So I'd have the coal producer paying the tax and the oil producer paying the tax, and of course they're going to pass it on to each level of the economy, and it's going to get to us, of course, and that's going to instantly make fossil fuels more expensive, as they should be, and wind and solar will come down as it should, and in the end, we're going to be okay. We're going to be able to do this. But what's going to happen is a cap and trade system. This is a derivative, as you know. Most of the part of the country that has it, the northeastern states and the northwestern states. Midwest is just about to announce in spring of this year. They haven't settled on their reduction, their cap yet, but the states are pulling the federal government along, trying to get a leg up with a cap and trade system. Most of them are auctioning off half of the allowances and giving away half of the allowances. They're using the auction to fund their energy efficiency programs. I think that's how it's going to go. Democrats love markets. Republicans love markets. They're just all over each other with respect to this. I worry a little bit about it because it actually is a derivative. You know, it's a contract. It's a derivative. And it's the kind of thing that hedge fund people love to bundle and sell and so forth. And I worry a little bit about manipulation. They have had some trouble with that in the UK market, as you know. But this is the way it's going. And it's coming real soon. I think before the 15th Conference of the Parties in December of this year, I predict we'll have some kind of federal cap and trade legislation. I'm going to kind of wind it up, but I've got here a few slides on what Iowa is doing, the policies that we think make sense. Many of them save money in dollars per ton of CO2 saved or avoided. They're negative costs. They can get real significant reductions, many of them, and so we're trying to move that way with legislation. It's a hard sale, though, and we're going slowly. We believe the country, DOE has said the country is heading towards 20% wind. If the country is heading towards 20% wind, we think Iowa is heading towards 60% wind, and that we'll be exporting a good portion of that, which means a better grid will be needed. And so we've been evaluating that. That's an investment. That's going to cost money. In a credit crisis, we need to find the money in order to invest in that. Cellulosic biofuels could be a huge savings for Iowa. They're figuring the subsidy will be $1 a gallon on that. I'm not sure. I'd like to see it go without subsidies, but it can't, at least right now. Nuclear power, I voted against it, but my committee was adamant that if you're serious about climate change issues, you can't rule nuclear power out of the mix. So for Iowa, we're planning for relicensing the one existing, I don't like this plant, but it's Duane Arnold Energy Center. It's an old pressure water reactor type of system. They want to relicense that when it was scheduled to be decommissioned in 2013, and they want to build one new nuclear power plant between now and 2020. And of course, you get big bang for your buck in terms of greenhouse gas reductions in millions of tons of CO2 equivalent. In summary, I really do believe there's an enormous economic opportunity here if we just stop moaning and complaining and try to get creative about how to do it. California certainly is a leader in that regard, and many of us look to you to continue your leadership in that. If you're talking about biofuels, there's going to be considerable water required based on the work that I showed you here, and local water problems created by the facilities. But I think they're here to stay. About the best thing I can say is that maybe we can view it as a bridge to a better, it's an infrastructure and a bridge to a better, more sustainable technology. Hopefully that's cellulosic biofuels in the future. The water quality impacts are huge. Every time you put your flex fuel vehicle up to the pump and pump a gallon of ethanol into your car, it's equivalent to about 8 grams, for every gallon of flex fuel, about 8 grams of nitrogen fertilizer going down the Mississippi River to the Gulf of Mexico. It's about 20 to 40 pounds of soil eroding off the land for every gallon of flex fuel you put in your vehicle. Cellulosic ethanol, I think, promises a better performance. At least that's what our committee thought. The energy bill of 2007 will require a major land expansion, and this whole question of land supply, indirect land use, is huge, and we haven't come to grips with that yet. This will cause large increases in nitrogen, and Europe and US are both trying to decide what to do with this. I don't think it's clear how we're going to go in the future. The picture's still a little bit like Vanna White turning the letters, but I do think, I am confident that we can get to a more sustainable energy mix that involves a lot of energy conservation and efficiency, a lot of renewables, and much less fossil fuels in the future. Thanks very much for your attention.
Thanks, Jerry. That was a really interesting and informative presentation on our different energy options and environmental impacts. We have plenty of time here for questions. Is this working? Because I can move this around
working.
for questions for Jerry. Gary.
Gary.
Soil is not a renewable resource, Jerry, and you just showed us there's an enormous erosion cost. I mean, corn, you know how corn is. It's not the greatest crop to grow.
No.
For any purpose.
Any row crop is bad, but corn is maybe the worst.
I mean, that's right. So one is talking about depleting a resource there, the soil, which is not going to be replaceable at any finite amount of time. That didn't get a lot of immediate time in your slides, but you did mention it a couple of times. What are your thoughts on that?
Well, you're right. Much like I was chiding Nebraska for using the Ogallala, the corn belt that I showed, including Iowa, we were glaciated just in the last Wisconsinian glacial period. The Des Moines lobe came down throughout much of the corn belt. At that time, it took 10,000 years of prairie plant growth to build up this rich, unique Iowa soil that I mentioned to you, almost unique resource in the world, and we've lost, average over the whole state, about half of that now. So it is indeed non-renewable, as you say, much like the Ogallala aquifer, and that's why I think that we can't continue to do it the way we're doing it. Yes?
So you were also talking about the land cost of the oxidation, but that's
Yes.
a one-time cost, isn't it? It's not like the soil flowing off. So it depends on how you amortize it. If you think of something sustainable, the initial cost implications goes to zero in the limit, doesn't it?
It's a good question, and you're right. You'd have to, in the life cycle assessments, they have to amortize that much like any other commodity and amortize it over to get an annualized cost. Yes, and they do that.
Let's get this one.
Is there any reason you haven't mentioned using or growing algae on wastewater in marginal land?
No, and I imagine at LBL you have a lot of good projects on algae for biofuels, and that is an attractive alternative. But honestly, I don't know much about it, and our report didn't deal with it, so it's my omission.
You'd mentioned the effects of land use. I have a friend whose brother is a farmer in eastern Washington and grows wheat, and wheat prices have gone up because many people are abandoning growing wheat to grow corn. And so this sort of secondary effect, have you included those types of things in your models?
I haven't, but the economists' models do. I would say, if I understand their work correctly, and that's a big if, but if I do, it's really a land supply issue. You know, the amount of land is finite. So in a way, it doesn't matter that corn is a food crop, you know, because as you say, it's whatever you use the land for that was being used for food can cause prices to go up and cause shortages. It's a land supply issue. It's all about the land, I think. And I believe that's how what the models show too. It's also the reason that, you know, I mentioned that most of the economic models that I viewed indicate that it's not direct, though it's more complicated than that. So by dedicating corn to ethanol instead of corn to feed or food, the price of corn does go up on the world market for food, but it's not a one-to-one kind of thing because there's other substitutions that can occur.
So I don't really understand the problem with this indirect land use, because the DOE and other people talk a lot about using low quality land for growing switchgrass and all these crops that is not used for agriculture right now. So then there is no indirect land use, to my understanding. And the second thing, looking at the strategies to change, it seems very car-based to me, which might make sense in a rural area, but in a dense area like the Bay Area, how about public transportation and promoting that much more?
The first question regarding land use, it's because the land that was marginal, let's say the savanna in Brazil, was storing carbon. And then when you convert it to grow corn for food, let's say, then it emits carbon. So the net effect of that is it's not the land is in short supply, it's the emissions from the land that's the land supply issue. And could you repeat the second part of your question? I didn't catch it.
I want to ask about public transportation instead of using cars, because
Yeah, I didn't have time for it, but public transportation is a huge part under energy efficiency, and most of the studies indicate, including ours, that we have to kind of replan our cities and have bundled growth in smarter cities in order to really get big improvements in automobile use. You're absolutely right. Yes.
You mentioned early on that about nearly 50% of the corn is used for feed, and it seems like we don't know how to make cellulosic ethanol yet, but cows certainly know how to eat grass, and if we change the way we feed our animals, we could free up a lot of supply of corn. And to what extent is research being done on how to shift away from feeding animals, like we could all become vegetarians, for instance, and, you know.
We all should be vegetarians, first of all.
Some of us are.
You're absolutely right. And there is, I'm not an expert by any means, but there is a lot of research going on trying to get animals to be able to eat other crops that don't, that make for fewer greenhouse gas emissions in the life cycle. Even the DGS, the dry distiller grains that I showed, that's very oily, And if you're not a ruminant animal, you have trouble digesting that. So the pigs won't eat it, for example, and we have 18 million pigs in Iowa and 3 million people. You know, it's a 6-to-1 ratio. The ones in Minnesota claim they can't tell the difference between the pigs and the people in Iowa anyway. But so there is a lot of research going on in that, and the dry distiller grains are a byproduct of the ethanol production, which